research paper on Tycho Brahe, Galileo Galilei, and Johannes Kepler. All three of these scientists were studying the motion of the planets and the characteristics of the planets and the stars, and trying to determine whether the sun was the center of the solar system or the Earth was the center of the solar system. If you recall, Tycho Brahe was very determined to prove that the Earth was the center of the solar system. And Tycho Brahe had the best data of the time. Remember, the high-tech data of the time. This was the stuff everybody wanted to have. And Tycho Brahe had the best data. He also had the best people working for him. Galileo was a geocentrist. He was a heliocentrist. He thought the sun was at the center of the solar system, and he tried his best to prove that. And as you found out, he was put on trial by the Inquisition and put under house arrest for the rest of his life, and where he died, and he turned blind, but he kept studying science. Kepler was Tycho Brahe's student, knowing full well that there were some implications that would happen to him if he wrote and professed that the sun was the center of the solar system. So keeping that in mind, Kepler also was an amazing scientist, an amazing mathematician, and he understood data. And the story goes that when Tycho Brahe was on his deathbed, there were some suspicious ways of how people thought Tycho Brahe died. Some people thought he was poisoned. Some people thought he died of a urinary tract infection. But nevertheless, Tycho Brahe was on his deathbed for some reason. And Kepler, his most famous student and best student, the story goes that Tycho Brahe made Kepler a promise that if Tycho Brahe gave Kepler his data, Kepler would use that data to prove that the Earth was the center of the solar system. Well, Tycho Brahe wanted that data. So the story goes, Kepler wanted that data. So Kepler, the story goes, promised Tycho Brahe that he would use that data to prove that the Earth was the center of the solar system. Kepler tried to keep his promise, but when he got the data, he waged his war on Mars. Now, if you don't have a piece of paper or Notability open to take notes, you should take notes, because this is important information that you'll have to use to take quizzes and do other things as we go through this. Why did he wage his war on Mars? Why Mars, not other planets? Well, because Mars was a planet that Tycho Brahe had the most and best data on. Mars was probably the most studied planet of the time. So Kepler got Tycho Brahe's data, and he started analyzing. He analyzed Mars first. But he not only analyzed Mars, he analyzed the other planets also. By understanding Mars and the other planets, Kepler was able to develop 3 laws of planetary motion that fit every planet in our solar system. His first law is that planets move in ellipses with the sun at one focus. Now, what do we mean by that? 2 important phrases: move in ellipses and the sun at one focus. You have to remember, this is a time when people thought that the heavens were perfect and that the laws, the physical laws, the natural laws of the earth did not pertain to the heavens at all. That what happened in the heavens was different than things that happen on the earth, that the heavens were perfect. Well, what is an ellipse? Another term for an ellipse is an oval. Let's take a look at what an ellipse actually is and how it's made. Start off with, I have a piece of paper, and I have a push pin in the middle of that piece of paper, and I have this string. A circle has one center. Actually, well, let's make this circle. So I'm going to make a circle. Try and keep my pen exactly in the same angle as we go around here. And there is a perfect circle, right? With one center. If we measure that circle as best we can with a ruler, we'll see that it is the diameter on every side. That's about 20.5 inches there. We go this way, that's about 20.5 inches. That's a pretty good circle. But now, what is an ellipse? An ellipse is really a circle, but the center of the circle has 2 centers. So now what we're going to do, we're going to have 2 push pins. We're going to move them apart. maybe something here. I'm going to put another pin here. So actually this now has two centers. Let's see what happens. I'm going to take this same string, same length of string, and the same pen. Come out here. We draw this. This is the exact same length of string that we had before. It looks like a circle, but it's not exactly a circle. Let's take a look and measure the centers, the diameters. This diameter is about 15, and this diameter is about 16 and a quarter, almost 16 and a half. So it's not a circle, it's now an ellipse, it's an oval. Let's extend this out even more so we can see what happens. Let's put this all the way out to here, this one all the way out to here. Let's make sure my string can fit around there. We got a little too long there. Let's move this in a little bit. Here, let's see if my string will fit there. There we go. Now, we have these two centers. I mean, the ellipse has two centers. Let's see if we can draw this. Now, this definitely looks like an oval or an ellipse. Again, whoops, came off the string there. Let's continue on. So there's my ellipse. This is the exact same length of string that I made for all these, the circle and the two ellipses. Notice the further away the centers go, the more oval it becomes. This is called eccentricity. I'm going to come back to this in just a little bit. Right, so an ellipse has eccentricity. What do we mean by eccentricity? Eccentricity means off-center. An ellipse actually has two centers. Now a circle is actually an ellipse, except for a circle, the centers are on top of each other. So there's only one center of a circle. What happens with, in order to make the ellipse, you take those two centers, again, this large circle, we initially had one push pin right there. We're going to split that one point into 2 points. So that one point becomes 2 points, and then we put those points further and further away. And so when something is eccentric, we call it off-center. For math, the more eccentric the circle is, the more those two center points are further away and the more oval or flattened out that becomes. If something is eccentric, like we call a person eccentric, they're odd, they're different, they're not normal. And so with this one statement right here, move in ellipses, what Kepler is saying is that the heavens are no longer considered to be perfect. They're actually odd, they're off-center, they're strange, they're different, they're not normal. And so he's saying the heavens are not perfect anymore. Remember, this is a time when people thought the heavens were perfect. Everything in the heavens had to be in circles because circles were perfect. But Kepler proved that it was not. The other thing is the sun is at one focus. Let's take this, we're going to use this smaller ellipse here so we can tell it's the ellipse. So what Kepler is saying is that the sun is that one of these little, we'll say this is the sun. This is an exaggeration, a huge exaggeration, but we'll see if it goes. So the sun is at one center. There's nothing over here, but the sun is here. It's the sun's gravitational pull that caused the planet to move around the ellipse. Kepler didn't know that at the time, but now we do. So with that, by putting the sun at the center, no longer is the Earth the center of the universe, but the sun is at the center of the universe. We'll say the solar system is at the center of the solar system. So with that, he moved the Earth from the center of the universe to the center of the solar system. So he moved the Earth from the center of the solar system just to be the third rock from the sun. The sun is now at the center of the solar system. The Earth is just like every other planet. The Earth is now just, as they say, the third rock from the sun. Earth is no longer the center of everything. The sun is the center of the solar system. Just with that one law, Kepler has defied huge amounts of things that the political system and the social and society at the time believed was true about their lives and who they were. The heavens are no longer perfect, and the Earth is no longer the center of the solar system. The sun is the center of the solar system. But Kepler did not stop there. That wasn't enough for him. There was more. The second one is that planets sweep out equal areas in equal times. Now Kepler just didn't make this up. He had the data to prove this. There was without a doubt this is exactly what happens. And in fact, we've seen something like this in the lab that we've done in circular motion. If you remember the stopper on the string, stopper moving in a circle. If we have that stopper moving in a circle at a certain radius, and we pull the string in to make the radius smaller, remember what happened to that stopper. If we have a smaller radius, it caused the stopper to move faster. Well, let's take a look and see what that means about sweeping out equal areas in equal times. Again, let's take a look at this paper. Again, this is an exaggeration because the sun isn't really that far off the center. It's actually somewhere in here, but we're going to use this to prove a point. Let's say, for example, we have a planet right here, like the Earth, and one day the Earth moves to that point right there. It moved through that distance. Well, sweep out equal areas in equal times. If we take a line from where the sun is and connect it to the Earth at its starting point, we take another line, connect it to the Earth at its second position. In other words, let's say this is like 1 day time period. In 1 day, the Earth will move that far. The area that it sweeps out is this area. We'll call that area 1. Now, what Kepler says, excuse me, if we have that same planet like the Earth over here, and it moves this exact same distance, we'll say that distance right there. The area that it sweeps out is this area right here. This area is not even close to this area. But Kepler is saying his data shows that the area swept out in the same time period must be the same because he has the data to prove it. So what that means is, in order for this planet to sweep out the same area in this time period, that the distance has to be much, much larger. So now if we sweep out from this time period, now this area, we'll say this is area 1, this area 2, area 1 must equal area 2. In order for the planet to sweep out equal areas in equal times, this planet in the same time period, this distance right here, this is 1 day, just like this is 1 day, this distance must be greater. So what Kepler is saying is that as this planet moves closer to the sun, it moves faster, which is exactly the same thing that happened with a stopper moving in a circle. We changed that, we pulled that string in, and the radius got smaller, the stopper moved faster. So what Kepler is saying is that planets speed up as they get closer to the sun. This is exactly what happens on Earth. Exactly what happens to objects moving in a circle or circular path. We'll say circle on Earth. Even though we know the planets don't move in a circle, move in ellipse, but the same phenomenon is true. In other words, what's happening in the heavens with this physical phenomena is the exact same thing that happens on Earth. What Kepler is saying with this is that the same physical laws that happen on Earth also happen in the heavens. So the same physical laws that occur on Earth also occur in the heavens. So what Kepler is saying, there's no difference between the physical laws on Earth and the physical laws in the heavens. They are the same. They are no longer different in any way. The same laws apply to both. Remember, this is a time when people thought the heavens were significantly different than the Earth, that the Earth's laws were separate from what happened in the heavens. Kepler's third law, which I think is the most amazing law, even though these had some huge social and political and societal effects on people. The third law was just a mathematical law. He analyzed all the data of the planets orbiting the sun, including the Earth, and he found out that every single planet that orbited the sun had something constant about it. And how he came up with the equation was just amazing, because it's not a simple equation. What he found out was that if you take the period of the planet, which is the time it takes the planet to go around the sun in 1 year, and every planet has a different period. Some planets like Mercury and Venus have shorter periods than the Earth. Jupiter, Saturn, and so on have longer periods than the Earth because they're further away. If you take the period of a planet and square it, divide it by the distance, which we call the orbital radius of the planet cubed. This is the distance the planet is from the sun. No matter which planet you can use Mercury's period and Mercury's radius, or the Earth's period and the Earth's radius. If you square it and divide it by the cube of the distance, you'll always get the exact same number. No matter what planet data you use in there, that K represents a constant. So no matter what planet you have, its period squared over radius cubed is always going to be the same. Now you've heard, hopefully you've heard, or if you've not, maybe you can understand this, the mathematical theorem. If A equals B and B equals C, then A equals C. So if every planet has this constant, then this must also be true. If we take the period of one planet, square it, over the radius of that same planet cubed, that must equal the period of the second planet squared over the radius of the second planet cubed. Both of these are forms of Kepler's third law of planetary motion. And it's amazing how he was able to come up with that. The data processing that he had to undergo. He didn't have computers or any smartphones or iPads at the time. He had to come up with that completely on his own. And this is Kepler's third law. On Wednesday, we will expand on Kepler's third law. We'll actually use this equation and see how it works. Also, you are going to have a quiz on Wednesday over Kepler's 3 laws of planetary motion. And part of that quiz might be 1 or 2 questions involving Kepler's third law of planetary motion. There's no assignment today. It's important that you have these notes down and understand what this is, because we'll be expanding on this and using this on Wednesday. Thank you very much.